The correct answer. A thermodynamic state function is a quantity.
Thermodynamic state function is a quantity. Okay, Hishma got disconnected. Anyone? Mariam, Samaira, Sarah, Aisha, Ifat, Matthew.
Sir,
What will be the answer? Yeah, no. What will be the correct answer?
Second.
Second, whose value is independent of path, right? Whose value is independent of path. Okay. Similarly, for the next question, Mariam, can you read that?
For the process to occur under adiabatic conditions, the correct condition is?
Yes, what is the correct condition?
Q equals to 0.
Q equals to 0. Yeah, third option. Yeah, correct. So, enthalpy of all standard form, this will be also you know. Tell about this question, 6.4. Maybe Samaira, you read the question, 6.4.
Delta U of combustion of methane is minus X kilojoule per mole. The value of delta H is.
So what do you think? How will you do this? Okay. So Samaira, what has been asked? Samaira, what has been asked?
The value of delta H.
Okay. Okay. Right now, you don't know how to approach this question. Yes or no? Or you know?
No, I don't know.
Right now, nothing is coming in your mind. Okay, fine. So they have asked you to calculate the value of delta H. And what is given in the reaction? What is given in the question?
Combustion of methane is minus X kilojoule per mole.
Yeah. So they have given delta U, right?
Yes.
So have we not learned the relationship between delta H and delta U? Or have we learned? You remember this phrase? Relationship between delta H and delta U?
Yes, sir.
Yes. Okay. So it is somewhere there in your notebook, right?
Yes, sir.
Now, but there you will recognize that you need the reaction. So you have to write the reaction and what? Delta H is equal to delta U minus delta Ng upon delta NgRT, right? So number of moles of gas, you have to see what is the change in number of moles of gas, and then you can calculate what is the delta H for the reaction, and it is minus X. So you may be getting some value. You have to know. Okay, fine. Maybe do this question. No? 6.4. Try to find what is the relationship in your notebook. Okay, the relationship between delta H and delta U, and then tell me what is the equation you are getting. What is the equation you are getting? Then I can help you. But please be quick in the feedback, okay? Let me know if you have got the equation. Let me know if you have got the if you have put in the value of X or something. If you have written the equation, the chemical equation. Yes, please find the relationship in your notebook. What is the relationship between delta H and delta U? Excuse me. Yes. Did anyone find what is the relationship?
Delta H is equal to delta U plus NgRT.
Delta U plus NgRT. Delta NgRT, right?
Yes.
Okay, fine. Now, also write the reaction. What is the combustion of methane? What will be the chemical reaction for combustion of methane?
It is CH4 plus 2O2 gives CO2 plus 2H2.
CH4 plus O2. It is going to give me
CO2
CO2
plus 2H2.
plus H plus 2H2O. Plus 2H2O, right? Yeah, 2H2O. Okay, fine. Now, from this chemical reaction, we can find delta Ng. So the products minus reactants, final minus initial. So what is the number of gases, number of gas molecules? So if you want to balance this, then you have to write 2O2, I guess, right? Yeah, 2O2. And since this water will be in liquid state, and if they have not given the temperature, you have to assume it to be 298 Kelvin. Okay, in the some of the questions they have not given the temperature, you assume it to be 298 Kelvin room temperature. So we have in the products, we have only 1 mole of gas, that is 1 minus 2 plus 1. There are 3 moles of gas in the reactant side. So this will be is equal to -2. Okay. And we have the relationship that delta H is equal to delta U plus delta Ng RT, right? Now delta Ng is what, how much? -2 RT. So I can say that this is equal to what? Delta H, it is equal to delta U minus 2 RT. Yes or no?
Yes.
Now you tell me, delta H is greater than or less than delta U? It is obviously not equal to, and it is obviously not equal to 0. So tell me, it will be greater than or less than delta U? Delta H will be?
Less than.
Yeah, correct. Because it is something less than delta U, because we are subtracting something from delta U. Okay. So again, easy questions. Okay. There are no tough questions in the chapter right now. There are no tough questions in the chapter right now. Now, please look at the 6.5 question. All of you, please stop writing now and look at the question number 6.5. Yeah. Now, in this reaction, they have said the enthalpy of combustion of methane, graphite, and dihydrogen are this, this, and this. 890, that is minus 893, 890, minus 393, and minus 285 kilojoule per mole respectively. The enthalpy of formation of CH4. They have asked for the enthalpy of formation of CH4. Okay. So what you have been asked? Enthalpy of formation of CH4, right? Yes or no, guys?
Yes, sir.
Now, this word enthalpy of formation of CH4, this will correspond to a chemical reaction, yes or no?
Yes, sir.
A balanced chemical reaction, a thermochemical reaction, yes or no? Yes or no,
Yes,
guys?
sir.
So this will be our target reaction. You remember how to do this now? We will assume, we will take this to be target reaction because this is something that we want to, calculate. Yes or no, guys?
Yes, sir.
Now, similarly, you have combustion of methane. This will correspond to a reaction. Combustion of graphite. Graphite is only carbon. This will correspond to a reaction. Dihydrogen will correspond to a reaction. Then you will have a series of reaction with their thermochemical property given. What is the thermochemical property given here? The enthalpy of combustion given. Now you will arrange these given reaction as per the target reaction. You will correspond. You will see whether which element or which species in the reactant and the product, and then you can multiply. You can also reverse the reaction, and you will arrange it in some way that it will make up, and it will, if you sum all those reactions, whatever you have arranged, it will get you to the target reaction. Now, whatever reaction you have written and however you have arranged it, you will just add them up to get the enthalpy of formation of CH4. You have some idea how to do this, yes or no? You have some idea how to do this or no? Hishma, Mariam, Samaira, Sarah, Matthew. Huh, guys? We have not done this type of, please say something na. Nahi bhi bol dijiye ek baar kam se kam. If you don't have any idea how to do this. Okay. Am I not audible?
So not really, sir.
What, Matthew?
Sir, you're audible.
Yeah, you're audible, but then about the question, I'm not really sure about it.
You're not really sure about it? Okay, fine. So in the notebook, you please go and look at the question that we did on the 29th of December. Calculate the enthalpy of formation from the following data. Calculate the enthalpy of formation from the following data. Calculate the enthalpy of formation of ethane. We did this after Hess law of constant heat summation. You go there in your notebook.
Yes, sir.
You found it?
Yes, sir.
There is ethane, and in the question in the NCERT, what do we have? Methane. Is there any difference? All the data that we have given, the reactions was given. Obviously, here the reaction is not given. I understand that much. But what are you saying? You will not be able to write the reactions? You can write the combustion of methane. You can
Yes,
write the
sir.
combustion of carbon. You can write the combustion of dihydrogen. Yes. What about you, Matthew?
Sir, I cannot find in the notes maybe because
No. Now see. When did you join?
last Monday.
You joined last Monday.
Yeah.
So last Monday was. So you have not watched the lecture?
No. Sir,
Hmm.
not really because I had a couple of things, a bit busy with school, but I like run through it a bit.
No. So you watch the lecture and then you will get to know, okay?
Okay, sir.
Because here they are asking about methane. The same question I have done in the classroom, and then I had ethane. Okay. So like in the process, there is not much difference. What about others? Sarah?
Yes,
Yes, Sarah. You found the question in your notebook.
yes,
Now you can do it.
yes.
Okay, fine. So see, all the questions that you are having here in the NCERT, they are not different questions. Okay, we have done similar type of questions. Don't worry about that. But acha, how many of you have read the notes till now of thermodynamics after the Viva?
Sir, I did.
You did read something?
Yes,
Okay.
sir.
What about others? Hishma, Samaira, Sarah? नहीं, so you have to read the notes. Now, please don't stop reading the notes. ऐसे आप लोग कीजिएगा नहीं काम चलेगा फिर. Okay. Now look at this question. The reaction A plus B, A plus B plus C, A plus B is giving C plus D plus Q. What is this Q? What is this Q?
Heat,
Yeah, this is heat. Okay, this is not a product. This is heat. Okay, Q is heat. Now tell me, heat is liberated, heat is evolved, or heat is absorbed in this reaction? Heat is produced in this reaction or absorbed in this reaction?
reduce,
Heat is produced. So the sign will be positive or negative?
positive,
Positive.
Guys, I can't deal with this type of behavior. Okay, now you please start reading the notes. If you don't know if the heat is evolved or if heat is absorbed, what is the sign? That's really a shame.
positive,
Positive. If heat is evolved, it is positive.
yes,
ये दो ही तो option है ना. Sarah, go back to
yes,
the notes. If heat is evolved, it is positive. Sarah, if heat is produced, yes, Sarah.
I guess.
You guess. Have you
I
please
said
look?
positive.
You said positive, na?
Yeah,
You're saying
my answer is positive. I'm not sure.
heat evolved will have positive sign. This is what you are saying, yes?
Yes,
Okay. Go to the second lecture, modes of transfer of energy. Sarah, okay. Get to modes of transfer of energy and let me know.
yes,
Okay. Do you see a diagram there? In between there is a system and there are some
yes.
arrows. What do you understand by that?
To the system it will be positive, from the system it will be negative.
Sorry, can you please repeat that in a very bit of clear voice? I could not hear you.
To the system it is positive, from the system it's negative.
Yeah, if heat is absorbed by the system, it is positive. If heat is evolved by the system, it is negative, right?
Negative.
Please start reading the notes, okay? Please start reading the notes. So the heat is what? Negative here. The heat is negative. And what they are saying about entropy change? The entropy changes. That means the delta S is what? Positive. Now look at the table that we made in the last lecture and tell me what is the option A, B, C, or there are 4 options here. Heat means was delta H is negative. Delta S is positive. Sorry.
Option 4.
Yeah, option 4. They did a mistake here. No? There should be 4 here, not 5. Yeah. Possible at any temperature. Both of these conditions are what? Favorable. Both of these conditions are favorable. Next. This question we have done in the classroom. And I think this question also we have done in the classroom. This is again the same type of question. You have been given delta U, and calculate the enthalpy. You have been asked delta H, right? So you will use the same equation, delta H is equal to delta U plus and delta NGRT. Yes or no?
Yes, sir.
Okay, same question, nothing different. Now, this question is not in your syllabus because heat capacity is not there in your syllabus. This question is also not there because heat capacity is not there in your syllabus. Then moving on to enthalpy of combustion of carbon to CO2 is 393. Calculate the heat released upon the formation of 35.2 gram of CO2. Read this question, Mariam. 6.11. Please read this question.
Enthalpy of combustion of carbon to CO2 is negative 393.5 kilojoule per mole.
Wait. What does this mean? This information. If 1 mole of carbon is formed, it will give me how much heat? 393.5 kilojoule. Yes or no? If 1 mole is formed?
Yes, sir.
Okay. And what they have asked, now read the question further on.
Calculate the heat released upon formation of 35.2 gram of CO2 from carbon and dioxygen gas.
Okay. So this 35.2, you can convert this 35.2 into number of moles, yes or no?
Yes, sir.
Okay. Now you will get some moles, right? You will get some moles. Now you have the heat released if 1 mole is formed, and then you have to calculate what will be the heat released if this much mole is formed of CO2. You can do this unitary
Yes,
method.
sir.
है ना, एक चॉकलेट का दाम इतना रुपया, 5 चॉकलेट का दाम कितना होगा? That type of question. Okay. So you have to understand what these values mean. The value means here. Okay, all of you understood, yes or no? Sarah, Hishma.
Yes.
Yes. Okay. Now again, this question 6.12, enthalpies of formation of CO, CO2, N2O, N2O4 are this much. Now again, all of this enthalpy of formation, you will write the chemical equation. What will be the enthalpy of formation for CO? For example, how will you write the formation equations? You will first of all write what? You will first of all write the product, that is enthalpy of formation of CO, then you will write CO. Then you will see which element is forming. Carbon is forming and oxygen is forming. So carbon is in solid at room temperature. Oxygen is at half O2. Okay, half O2. You cannot change the stoichiometric coefficient of the product because it should be 1 mole of product form, because the definition of enthalpy of formation says that the enthalpy change when 1 mole of a substance is formed. So you cannot change the number of moles of the product. Similarly, you will do the same thing with CO2. Then you will do the same thing with N2O. Okay, and then you will do the same thing with N2O4. Now you have a series of reaction. Then you have been asked find the value of delta HR. That means the enthalpy of reaction for the following reaction. This is our target reaction. Okay. Now what you need to do, you need to arrange these reactions in such a way that when you sum them up, you will get the target reaction. Then you will also write the delta HS here. You will also write the delta H of formation here, and however you have arranged these reactions, you will sum them up. Okay, you will sum them up. What things can you do while arranging them? You can multiply the whole reaction with any number. Or now, if you are multiplying any reaction with some number, you also have to multiply the same number to the enthalpy of the reaction. Okay, enthalpy of the reaction. Now, if you're dividing something, then you'll also have to divide the same number to the enthalpy of reaction. Whatever you're doing with the stoichiometry, you have to do the same thing with the enthalpy of the reaction. Okay, these things we have done earlier also. Now, the other thing that you can do is you can reverse the reverse the flow of reaction. Okay, that means you can reverse the arrow. The products will become a reactant and the reactant will become the product. Now in this case, what you will do, you will change the sign of enthalpy of reaction. Okay, you remember these points, yes or no, guys? Sarah, Samaira, Hishma?
Yes, sir.
Yes. Okay, next is given. Now read this question. This question is very small and we can do this right now only. Read this question, Samaira. 6.13.
Given N2 gas plus 3H2 gas gives 2NH3 gas. Delta H,
The enthalpy of reaction is equal to,
the enthalpy of reaction is equal to minus 92.4 kilojoule per mole. What is the standard enthalpy of formation of NH3 gas?
yeah, okay, fine. Now, when you write standard enthalpy of formation, okay, is this the reaction for standard enthalpy of formation of NH3? Is this the reaction? Because NH3 is forming here, no? Yes or no? NH3 is forming, yes or no, in this reaction? So is this the standard enthalpy of formation of NH3?
No,
No. Why not, Mariam? Can you please
because
elaborate on?
there are 2 moles.
Yeah, exactly correct. Very good. Huh? So you have to see these very little points. See here, 2 moles are forming. That is why it does not fit in the definition of standard enthalpy of formation of NH3. Okay, now what we need to do, we need to divide the whole equation by half, and then we will be forming the chemical equation which fits on the definition of standard enthalpy of formation of NH3. Now, if you are multiplying by half this whole reaction, or rather we are dividing by 2 the whole reaction, then we have to divide by 2 here also, and then we will get the standard enthalpy of formation of NH3. I think we did this type of question in the class also. I don't know whether the same also or not. Maybe same. Achha, again here you have some reaction. You need to arrange it, है You need to arrange it, and you need to calculate the standard enthalpy of formation of CH3OH. Next is you have again a target reaction. Okay, then calculate the bond enthalpy. Now in this case, we just have to calculate the bond enthalpy of CCl. Okay, delta H formation and enthalpy of change in the process. So you will get the delta H naught of the reaction. Okay, now this in delta H naught of reaction, what is happening? CCl4 is CCl4. All the bonds in CCl4 is broken and it is getting converted into carbon gas and 4 chlorine atom. 4 chlorine atoms. So we have 1 mole of CCl4. That means we have 4 moles of CCl bond. Yes or no? We have 4 moles of CCl bond. If I have 1 CCl4, 1 mole of CCl4. Yes or no, guys? 1 mole of CCl4.
Yes, sir.
Then we will have 4 moles of CCl4. That means what we need to do, when we need to calculate the bond enthalpy of CCl, then whatever is the enthalpy of reaction here, you divide that by 4, and that will be the bond enthalpy of CCl. This is what mean bond enthalpy. This is mean bond enthalpy. Okay. Next is for isolated system, delta U is equal to 0. What will be delta S? So for an isolated system, delta S is always positive. Delta S is always positive. Next question for the reaction here, 2A plus B is giving C. This question is something that you need to do. Okay. 6.17. You try this question. You try this question. In the next class, I will discuss this. In this question, this is important part. At what temperature will the reaction? How to determine this temperature? Now, it needs some practice. If you have not done this type of question, then you may not be able to do. But otherwise, please try this question. Okay. For the reaction, 2 chlorine is giving me Cl2. What are the signs of delta H and delta S? For delta S, I can obviously say initially we had 2 mole. Here we have 1 mole. So that is why delta S will be negative because the entropy is decreasing. We had more number of gases. Now we have less number of gases. Okay, we have less number of gases. What will be delta H? Delta H will also be negative because initially we did not have any attraction. Now something is being formed. Whenever you form some things, whenever there is an attraction, the delta H is negative. The delta H is negative. For a reaction, you have been given delta U and delta S. This is the reaction here, and calculate the delta G naught and predict whether the reaction may occur spontaneously or not. So delta G is what? Delta G is equal to delta H minus T delta S. Now in this reaction, you can see that delta H is not given. So what you will do, you will use this delta U, and again here temperature is not given, so you'll use the temperature that is 298 Kelvin. Okay, 298 Kelvin room temperature. Now delta U, And you need to find what delta H. So you have this delta H is equal to delta U plus delta NgRT, right? So we have this reaction. Now from this reaction, you can calculate the Ng. R you can take as 8.314 Kelvin. Temperature you will take as 298 Kelvin. Delta U has already been given. You will get the delta H value here, and you will substitute, you will plug in the delta H value here. You will put the temperature as 298. You will put the entropy as whatever is given, minus 44.1 joule per Kelvin, and then you can get the delta G naught. Now, if the delta G naught is positive, or it can be negative by whatever you are getting. If it is positive, that means it is non-spontaneous. If it is negative, it is spontaneous. Okay. So I think none of, I mean, in these type of questions, you don't have any conceptual gap, right? Yes or no? You know all these equations, correct?
Yes, sir.
है ना? So you can try these questions. Okay, you can try these questions. Don't be lazy. Okay, don't be lazy. Problems ऐसे ये मतलब आलसी मत बनिए. Next is 6.20. The equilibrium constant for a reaction is 10. What will be the value of delta G naught? So in the last class only, the last equation that we wrote was about delta G naught. You can directly plug in the values and get the answer. Okay, you have the equilibrium constant also, that is 10. You have the value of R, you have the value of T. Then next is the comment on the thermodynamic stability of NO given the two things. Okay, fine. Now this question, please look here and try to focus here. Look here and try to focus here. Okay. Now in this question, what is happening? They have been we have been asked to calculate what is, we have been asked to comment on the thermodynamic stability. Is NO gas stable or it is unstable? It is stable or unstable? So first of all, we will see what is happening when the NO gas is being formed. Okay. Now if the NO gas is being formed and we are liberating some kind of energy, if the heat is evolved, that means NO is stable. That means NO is stable. But we see the reverse is happening here. That when NO gas is being formed, we require 90 joule of energy. We have to put in the system 90 joule of energy. Okay. So the system is not liberating any energy, rather its energy is increasing. So that is why I can say it is a unfavorable. It is what it is, unfavorable. Now this can be favorable. I mean, and NO can be stable if NO is reacting with oxygen and it had some positive value here. Okay. So if its reactivity was low, but we can see the reactivity of NO is what? Very high. Nitrogen oxide can react with oxygen and it will give NO2, and it will also liberate minus 74. It will also liberate 74 kilojoule per mole of energy. Now, when it is liberating energy by doing a reaction, so it will not stay in the NO form. It will never stay in the NO form. What it will do? It will react with oxygen because it wants to lower the energy. It wants to lower the energy. That is why you can say that the NO is not stable, thermodynamically not stable. Okay, thermodynamically it is not stable, it is reactive. Calculate the entropy change in surroundings. Okay, entropy change in surroundings when 1 mole of H2O is formed under standard conditions. So we have said that delta H of formation is minus 286 kilojoule per mole. Now this is interesting. Please look here. Please look here, 6.22. So when 1 mole of H2O is formed under standard condition, okay, under standard condition, what is the entropy change? What is the entropy change? So delta S of surrounding, this will be equal to what? This will be equal to whatever the, I can say, Q of surrounding divided by temperature. Yes or no? We have written this equation. Delta S is equal to Q by T. Okay, fine. Delta S is equal to Q by T. Now, this is our small little reaction where the reaction is happening. And what is the reaction doing? It is liberating heat or it is absorbing heat? It is producing heat or it is absorbing heat in the reaction? When H2 is formed, what is happening? Tell me. Heat is evolved or heat is evolved, right? Yeah, correct. Heat is evolved. Yes, it is negative. It is evolved. Why is everyone's voice very low? Okay. Now, if heat is evolved, then where will the heat go? To the surrounding only? Yes or no?
Yes, sir.
Now you tell me about the surrounding. So surrounding is absorbing heat or it is, I mean, is the heat evolved by the surrounding or it is absorbed by the surrounding?
Absorbed by the surrounding.
Absorbed by the surrounding. Okay. Now it's the same amount of heat now, which the system is liberating, but in opposite sign. So what you can do about the Q of surrounding, you will write that as 286 kilojoule, right? Now 286 kilojoule heat is being evolved, and then you have the temperature, that is what standard conditions, that means 298 Kelvin. Now you can calculate, yes or no? Tell me. You understood this, yes or no? Tell me.
Yes.
All of you?
Yes, sir. Yes, sir.
Yeah, okay, so that is why we say that delta, sorry, you can directly write delta S of surrounding, it is equal to the negative of whatever the enthalpy of system is happening, okay, divide by temperature, okay. By negative, now negative, it is just present to change the sign of delta H. Now if delta H will be positive, for the surrounding, it will be negative. If the delta H is negative for the system, for the surrounding, it will be positive, okay. Now this is not essentially something that you can write, or you don't want to write, then you cannot write, okay, no problem in that. Let me know. So most of the, not most, all of the questions you should be able to do this, okay. So but please complete the NCERT, okay, please complete the NCERT. You have only how many questions? Some 22 questions, I think 22 23 questions, 22 questions, and then you will be having some questions in text questions, okay. You can do those also. They will be very little. I don't think it has many in text question. Yeah, there are examples only, so please complete the exercises and the in-text question of thermodynamics, okay. Let me stop sharing the screen and let us move on to the next chapter, that is equilibrium. Wait a second, I need to close this, otherwise. Yeah. I think it will be better now. Yes. All right, the heading equilibrium. Equilibrium. So we have come to the notion of equilibrium, and more specifically, we will be talking about thermodynamic equilibrium, that we wrote some type of definition in the thermodynamics class also, right? What is equilibrium? Where nothing happens. Yes or no? Where nothing happens.
Yes,
You
sir.
remember this? Yes. What is equilibrium? Equilibrium is where nothing happens. Now, exactly when we are saying about when nothing happens, that means it means that thermodynamically speaking, in terms of thermodynamic properties and thermodynamic state functions, nothing is happening. Nothing is happening. But let us say if I have something like, let us see if I have something. Okay, let me give you an example. Okay, so we have partitioned this one box into two different compartments, and we have placed some different type of gases here. Okay, we have placed some different type of gases. So let me place some gases here. Okay, now in this part of the compartment, in this part of the box, I'm putting glow gas. Now tell me, now if you are keeping it fixed like this, then nothing is happening, right? Yes or no? Nothing is happening. Guys?
No, nothing is happening because it is blocked.
Blocked, right? Blocked. Okay. Now again, when we say nothing is happening, but they will be moving here and there, correct, Matthew?
Yes, yes.
So macroscopically speaking, like macroscopically in terms of properties, I will measure what? I will measure the temperature, I can measure the pressure, right? I can measure the volume. Now these things will not be changing, correct?
Yes, it won't change.
It won't change. Okay. Now let us say what is happening here. Let us say that the red ones now they are hot. That is hot air. Okay. The red one is hot air. Okay. And this is completely, I mean, we have insulated this part. So oops, we have insulated this part. That means the heat cannot be exchanged between these two compartments. Okay, the heat cannot be exchanged between these two compartments. Now tell me what will happen. The temperature, let us say this is 25 degrees Celsius, and here the temperature is, let us say, 50 degrees Celsius. Okay, after a while, what we will do, we will remove this blockage. Okay, so as soon as we remove this blockage, what will happen?
They start reacting with each other.
No, these are not reacting with each other. These are not reacting gases. So they will mix with each other.
Yeah, they will mix with each other. Yeah.
Anna? They will mix with each other. When we don't have any compartment, then the red gases, they will come here. The blue gases will come here. They will be completely spread out. Okay, evenly spread out. Okay, and also there will be, now when the change is happening, we will be seeing that the temperature here, the temperature in this compartment, it will be what? It will be lowering a bit, and in this compartment, it will be rising a bit, right? So, like at the end, when everything stops, we can say that till when the mixing is happening, the temperature will be changing, right? Temperature will change. Right now, when the temperature will stop changing, after a point, it will stop changing. Correct? When they have equally distributed themselves over the box. Correct, Matthew?
Yes, it will change.
It will stop changing, na?
Yeah, it will stop changing at a point. Yeah.
Stop changing at a point. It will stop changing. Then we will say that now the equilibrium has been attained. Correct?
Yes.
Now the equilibrium has been attained. Now, this concept is very important, that when we are talking about something, when we are talking about an equilibrium, there should be one property, there should be one macroscopic property that should be constant. Yes or no? In this case, that property is temperature. Correct?
Yes.
So initially, like before removing, then also the temperature on each of the compartment was constant. So we said that it was in an equilibrium state. Now we disturbed the equilibrium. That means we removed that. Remove that blockage. Now the temperature started to change. That means now it is not in equilibrium. Something is happening. Some process is happening, right? So we have learned all about process and the thermodynamics. Now we are coming to a stage. Now we will talk about equilibrium. What happens after the process? Okay, what happens after and before the process? So we will always have, now in this whole chapter, there will be always an initial state. There will be some initial. Okay. Now then we will change something. Okay, and then we will have some final state. Okay, change, and then we will have some final state. Now we say that it is initial. We call this as initial only. Then the change is change only. Okay, and for the final, we don't say it as final. We say that it is the equilibrium state, because we are not doing anything after the equilibrium has been achieved. Okay, after the equilibrium has been achieved. Although in initial state also there was an equilibrium, but we are not calling that an equilibrium because we are going to disturb that equilibrium, right? So this will be a constant theme in this chapter, that initial, change, equilibrium, initial, change, equilibrium, initial, change. We will be having something initial, then we will change something, then we will have equilibrium. Okay, right? Now there are, okay, you understood the concept of equilibrium. What is equilibrium and how are we going to define equilibrium? Define in the sense in a system. In a system, how we are going to define? We should be having some property which is constant. Did you get till here? Yes or no?
Yes, sir.
Yes,
Whenever
sir.
you are talking about equilibrium, you will think of what property is constant, what measurable property is constant. Okay, so that notion should be in your head whenever you are talking about equilibrium. What is getting to be constant? What is getting to be constant? Next is the equilibrium. In your book, it has been classified into two types, that is physical equilibrium and chemical equilibrium. So that means the equilibrium which mostly considers and mostly is concerned with the physical changes. So we call that physical equilibrium. And then you have those involves chemical equilibrium. So chemical, I will say, equilibrium, the chemical equilibrium. Okay. Now, what do you think? What can be there in the physical equilibrium? Physical equilibrium, you can have what? if you can have liquid to vapor changes, right? You have liquid. Now this equilibrium sign is shown like this. Okay. One more thing. Is the temperature constant or is it zero? It is a constant, right? It's not zero, right? When we achieve an equilibrium, it is constant. It is not necessarily zero, right? The temperature.
Yes, sir.
So please keep that also in mind, that when we say about a constant, it does not mean that it is what I would say, zero. Okay. So now liquid, it can change to vapor. And the liquid vapor equilibrium, it is shown by this arrow. This arrow is for equilibrium. Okay, this arrow is for equilibrium. Then you can have, okay. Now what will be same here? What will be same? If you have liquid vapor equilibrium, the vapor pressure or the pressure will be constant. Let me tell you how. This is a closed vessel. Okay, it is not isolated, it is closed. Fine. We have water here. Okay, fine, everyone. Any problem till here? No problem. Can I move? Please tell me, guys.
Yes.
Okay, fine. Now see, if you have this much water, some of the water, it will get evaporated, yes or no? It will get evaporated, yes or no?
Yes, sir.
It will get evaporated. Okay, fine. It will get evaporated, correct. Now, if this water was, in a very closed pack, then the rate of evaporation will be high, it will be very low. The rate of evaporation will be high or low? Tell me. No idea?
Be high because it's in a more tighter space.
So the evaporation will be high. Why?
Because it's in a more tighter space, so it can like
it can
the temperature in the container can increase faster.
No. We are not increasing the temperature now. How are you saying? Acha, tell me. Simple question. Let us move back to your kitchen. We have a open vessel in which we have water. Okay, in which we have water, and we have a closed vessel in which we have water. Which is going to get evaporated more easily?
The closed vessel.
The closed vessel is going to evaporate more easily.
Oh.
What do you guys think? Heshma, Mariam, Samaira, Sarah?
Open one.
The
Open one, na? See, these girls have been there in the kitchen, right? Okay. Now, if the open one is getting evaporated more easily, right? Open one is going to evaporate more easily. Now you can say that. No, you can delete this. Now you are able to answer. What will happen if I have? Okay, I have water like this. Okay. Now, if the compartment is very small, पानी मेरा चूने लग गया. What has happened here? Oh. Yeah. So if you have relatively closed vessel or a small vessel, then this water will be getting evaporated and it will be forming water vapor. Correct? Yes or no? Yes or no, guys?
Yes, sir.
Now this will be leading to some pressure due to the water vapor. Correct?
Yes, sir.
Now, what I will do, I will increase the volume here. Okay, as soon as I will increase the volume here, what will happen? Tell me. See. Now the water does not know that the surface water, it does not know the volume has been increased, right? volume has been increased. So let me say what happens. So this is time, I will say, and I'm increasing, right? I'm increasing the volume. I'm increasing the volume and time, and here is the pressure. Okay, the pressure due to H2O. Now it was constant when the volume was at certain point. Now what I did, I increased the volume. So pressure and volume has inverse relationship, yes or no?
Yes, sir.
Now what will happen? The pressure will drop, correct? The pressure
Yes,
will
sir.
drop now. Now if the pressure is dropped, that means it is not in an equilibrium state, right? It is not in equilibrium. Then what will happen? Slowly these water molecules, they will go up, they will form some more space in the lower levels on the surface of water, then more water from the surface, they will start to evaporate. Okay, now if more water is getting evaporated, that means the number of moles of water is going to increase, right? And why is there a why more gaseous molecules are being formed? Because the volume has increased, right? Volume has increased and they can move over a large area. Now as soon as the volume will increase, the number of moles will increase because more evaporation will happen. Now if the number of mole will increase, what will happen? The pressure will also start to increase, and slowly you will see that it will regain the same pH2O. Okay, now again here we saw that initial, then there was a change. We saw what is the change here, what is the effect due to that change, and then we got an equilibrium. Okay, now in this case that is vapor pressure, and we have vapor liquid equilibrium, we have vapor liquid equilibrium. What is constant? The pressure of H2O is constant, right? The pressure of H2O is constant. You got this idea? Yes or no? Tell me.
Yes, sir.
Yes, sir.
Okay, fine. So let me delete this and let me write. The pressure is going to be constant. In the bracket, I'm writing what is going to be constant. What is going to be constant? Now, secondly, you can also have. Secondly, what you can have, solid liquid equilibrium. In solid liquid equilibrium, see, in solid liquid equilibrium, what is going to be constant? The melting point is going to be constant. Okay, the melting point is going to be constant at a constant pressure, I would say, at a constant pressure. Now, there can be another type of physical equilibrium, that is, if you have, let us say you have some solute, okay, and it is getting dissolved into a solution. It is getting dissolved in the solution. So what I can say it is solute only, but inside a solution. Okay, then what is going to be constant here? The concentration. The concentration is going to be constant here. Whenever you are going to achieve an equilibrium, the concentration is going to be constant. And if the concentration is not changing, that means it is an equilibrium. I will explain this solute and we will also do a question here. Okay. Then what you can have similar type now. You can have a solid solute, or you can have a liquid solute, or you can have a gas solute. There can be other cases of solute and solution equilibria. Write this down. Let me know if you're done. Okay. Then we will understand this point.
Done, sir.
Done. Okay. Now let us see what happens if I dissolve something. What happens if I dissolve something? So we have water here, right? We have water here. And then what did we do in the process? We added sugar. Now, initially the concentration of sugar was what? 0. Yes or no? Initially,
Yes,
the
sir.
concentration of sugar was 0. Now, as soon as we added, we did some change. Yes or no?
Yes, sir.
Now, tell me, that change can be seen in the change in concentration. Correct? When we
Yes,
are
sir.
doing now, and when I will say the equilibrium is reached, when the concentration stops changing, right? Yes or no?
Yes,
When
sir.
the change in concentration is equal to 0, we will say that change in concentration, not the concentration is equal to 0. Okay, the change in concentration will be equal to what? 0, then we'll say that equilibrium has been achieved. Correct? Yes or no, guys?
Yes, sir.
Okay, again, see the same pattern. Okay, I will be telling you again. Initial, this is the change, and then you have the equilibrium. Okay, so what is the parameter that we are looking at right now? The concentration. We will be looking at concentration here. Now, let us do a simple question here. Okay, but don't worry, ऐसे अभी 1 घंटा हुआ है, सर आप सवाल कराइएगा. We'll understand this question. Yeah, please write this question now. It is a long question, but don't worry about it. Okay, you focus on initial change equilibrium. Initial change equilibrium. Ice, है ना? We can say ice. We will focus on ice. Let me know if you're done writing the question. Okay, then we will explain that. Please also don't blindly write. You can also read and write. Okay. ऐसा नहीं कि क्वेश्चन लिखने के बाद फिर से आपको पढ़ने की जरूरत पड़ रही हो. Done, guys?
No, sir.
No, still writing. Okay, write this question. You don't have to do it. Okay, write this.
Done, sir.
All of you done?
Yes, sir.
Okay, fine. Okay, I want to introduce you to a word that you already know, that is dissolution. You know what is dissolution? Okay, you know what is dissolution?
The process of dissolving something into
Dissolve
a
is
solute.
something. Yeah, correct. Dissolve something. And there is one word which is crystallization. Do you know what is crystallization? Crystallization will be the process of forming of crystals, right? Solid. Correct?
Yes, sir. Yeah.
Okay, fine. Now, dissolution and crystallization. Okay, keep this in your head. Dissolution and crystallization. You take some water. You take some water here. Okay, you take some water. You add NaCl. Okay, so let us say that you have taken 100 ml and you have taken NaCl 1 kg, or rather, let us say even 0.5 kg. What will happen? All of the NaCl will be getting dissolved.
No,
No, right?
some of it will be in the down because it's fully concentrated.
It is fully concentrated. But let us look at this more closely. Okay, let us look at this more closely. So let me say now NaCl is white, but let me give it a pinkish kind of tint. Okay. So let us say that this is your NaCl. Okay, this is your NaCl. What is going to happen? The water molecules will come. They will interact with. So we have sodium positive, right? So sodium positive, it will interact with what? Oxygen of the water, because oxygen has delta negative, 2 delta negative charge, right? And it will take up, it will catch this Na positive and it will take it away, and then it will surround the Na positive with different H2 molecules. Okay, so I have shown this as H2O. You can see that this is oxygen, this is oxygen, this is oxygen, and the legs or the hands or the ears, whatever you want to say this, those are what? Hydrogens. Okay. Now, when it will surround it like this, now we will say that we cannot see Na positive because it has lost its identity, right? NaCl has lost its identity, and Na has been surrounded by water molecules like this. Then the chlorine negative will be surrounded by water molecules like this, because the hydrogen will have a positive charge, and they will surround the chlorine negative molecules like this. Okay, you understand now how the dissolution happens? Yes or no?
Yes,
Okay,
sir.
tell me. Okay, fine. Now, what do you think? What do you think? Let me ask you, what do you think? Let us say there were 100 different molecules of NaCl. Okay, 100 different molecules of NaCl. And out of the 100, let us say that 70 got dissolved. Okay, 70 got dissolved and 30 were undissolved. Fine. 70 got dissolved and 30 were undissolved. Okay. Any problem till here? I'm going really slowly. Please tell me yes or no. Any problem till here?
No, sir.
No. Okay, fine. Now, what do you think? Will these 30 be the same 30 that are undissolved always, or some of the 30 will be getting dissolved and some of the 70 they will be crystallized? Like what will happen from this 30 also? From in this 30 there will be water molecules interacting with it, so some of the water molecules will be taking up, some of the water molecules will be taking up and chlorine negative from the 30 which is undissolved, but from the 70 that has been dissolved, some of the water molecules they will lose the Na positive and Cl negative, right? So when they will lose the Na positive and Cl negative, NaCl will come together and they will form again solid. But overall, no, microscopically speaking, there is something happening. The changes are still happening. That means there is some dissolution happening, there is some crystallization happening, but overall, macroscopically speaking, the concentration of NaCl is not changing. You understand what is happening? Yes or no? Guys, you understand
Yes,
this notion? You understand now? See, for example, let us say that you have there is a swimming pool here. Okay, there is a swimming pool here, and so the capacity of, there are 5 persons who are, if you look overall the day, then you can say that 5 persons are there in the swimming pool always. So what does that mean? Does it mean that the same 5 persons will be there in the swimming pool? No, no.
No.
No. So what is happening? Some people are going away from the swimming pool. They are getting out of the swimming pool. Some people are coming in. But the rate of going out, the rate of out is equal to what? Rate of in. Yes or no? Hi guys.
Yes.
Now similarly, I can say now the rate here. What is two things are happening, right? Two things are happening because we can see crystal NaCl is present. That means obviously what that means. That means there is some crystallization happening and there is also some dissolution happening. Now, whenever crystallization and dissolution both are happening, then you can see that the rate of crystallization and the rate of dissolution is equal at equilibrium. Okay, at equilibrium, what is equal? Let me write the rate of crystallization is equal to what? Rate of dissolution. Okay, rate of crystallization, it is equal to the rate of dissolution. Now let us move back to this question here and let's see what is this telling us about. The solubility of iodine in water is this much. So this is one data that they have given. Then they have said that when 200 grams of iodine is stirred in 100 ml of water, okay, just put this as ml. There's no unit given. Okay, you can put this as ml. 200 grams of iodine is stirred in 100 ml of water till equilibrium is reached. Okay, what will be the mass of iodine found in the solution and the mass left undissolved? Okay, so this is one type of question that we have asked till here. So we will first of all calculate that. So we have initial 100 ml, right? Then what is the change? We added 200 grams of 0.2 grams of 0.2 gram of I2. Okay, and here this is the equilibrium that they are asking. What will be what mass of iodine is found in the solution and what mass is left dissolved? Okay, so what mass is dissolved and undissolved? Both of these things they are asking. Okay, now this will be helpful for us. We have said the solubility is equal to how much? Solubility is equal to 1.1 into 10 to the power minus 3 moles per liter. Okay, minus 3 moles per liter for iodine. That means it is equal to in 1 liter of H2O, 1.1 into 10 to the power minus 3 mole of I2 can be dissolved. Yes, you understand what is this data telling us? Tell me.
Yes, sir.
Okay, that means in 1 liter, rather than writing 1 liter, what I can write 1000 ml, right? Because we have been given 1000. We have been given ml, that is why 1000 ml. Then we have 200 gram. Can you calculate the moles? Number of mole of I2. This will be equal to how much? The given mass, right? The given mass by the molar mass. What is the given mass? Yeah. What is the given mass? What is the given mass? अरे given mass तो बता दीजिए. What is the given mass?
0.200 gram.
Yeah, 0.200 gram. 0.2 gram. What is the molar mass of iodine? You must not know. This is 254. Okay, 254 grams per mole. Now I can see that there are two things I can do. I can calculate the number of moles of iodine, and then I can calculate how much is dissolved or not dissolved. Or what I can do is I can convert this into grams, right? I can convert the solubility into grams. So rather than saying 1.1 into 10 to the power 3 mole of iodine is dissolved in 1000 ml of water, I can say in 1000 ml of water, 1000 ml of water, 1.1 into 10 to the power minus 3 into 254, because what is mole? It is 254 grams per mole. In terms of, if I want to write that in terms of what grams, into 254 gram of I2 is dissolved. Can I do this? Yes or no?
Yes, sir.
Yes, sir.
This is just one approach of solving the question. Okay, so let me just calculate this. 254 and 1.1. 11 ones are 11 fours are, then 11 fives are, then 11 twos are. 44, 55. This is how much? You get 4, then 4 plus 5, 9. Then you will get 7. Then you will get 2.1, no? 0.1 into 10 to the power minus 3 grams. Okay. So what is this equal to? This is equal to 0.02, no? Zero 0.2794 grams in 1 liter or 1000 ml. Correct? In 1000 ml. Then amount of I2 dissolved in can be dissolved in 100 ml. This will be equal to how much? 0.2794. This much is dissolved in how much? 1000 ml. So how much can be dissolved in 100 ml? This much gram is dissolved per 1000 ml, right? So in 1000 ml you can dissolve this much. So for 100 ml you just multiply this by 100, no? So multiply this by 100. Okay. Yes or no? Because you have, what is this? Amount of I2 dissolved in 1 ml, correct? This whole quantity. Yes or no?
Yes, sir.
Now if you just multiply that by 100, you will get that. So you will get 0.02794 grams can be dissolved in 100 ml. Okay, can be dissolved in 100 ml. And how much have we dissolved? We have dissolved 200 grams, 0.2 grams, sorry, 0.2 grams. So amount of I2 undissolved. This will be equal to what? 0.2 minus 0.02794 grams. Correct? Calculate this. Tell me how much is the value. Approximately, I can say 170, 0.172. 0.172 grams is undissolved, right? Tell me.
Yes, sir.
Okay. Now 172 gram is undissolved. Then what they are saying, they added how much ml? 150 ml, no? Yeah. After the equilibrium reached the gram of water, we added 150 of ml of water to the system. How much iodine will be dissolved now? Okay. So again, after adding, add 150 ml. So now amount of I2 that can be dissolved in 250 ml. 250 ml, it is equal to how much? 0.2794 divided by 1000 into 250, right? Into 250. What will be this equal to? We can cancel this by 4, no? Yes or no? And what I can write this as 0.28 divided by 4. So this will be equal to 0.7 or 0.07. guys, tell me. Uh, 7 4 is 28, 0.07, no? Because then 7 into 4 is equal to 28, and then we have 2 points, so 0.28. Yeah. Tell me, you understand these steps from here to here?
Yes, sir.
Okay, fine. So this much gram can be dissolved in 250 ml. Now you can see amount undissolved. Which is equal to how much? 0.2 minus 0.07, which is equal to 0.13 grams. Right? This is undissolved. Now, one thing I want. Oh, okay, fine. You want to write this? How much have you written? Tell me. How much have you written?
Done, sir.
Done. Okay. Now, this is something which will be very common. That conceptually equilibrium is going to be. Conceptually, it is not hard. Okay. Conceptually, at least it will not be hard. But yeah, numericals are long. Okay, numericals are long. You have to be patient. You have to be patient. You have to do calculations. Okay, don't please make up your mind that you have to do calculations here. And in examinations also, they will be only asking you regarding the I mean, they will be asking numericals from this equilibrium portion, thermodynamics portion. There may be some more theory part in thermodynamics, but in equilibrium there will be most of these will be calculation numericals. Okay, so please be ready for numericals in this chapter. Now, we have done one question for physical equilibria. It is not the major portion of your chapter. Now, I'm going to move towards the equilibria, which involves chemical systems. Okay, so please write equilibria in chemical systems. In chemical systems. Equilibria in chemical systems. Okay. Now, in this equilibria in chemical system, first thing is that we need to understand that what happens in chemical systems, we have reactions, right? We have reactions. Please don't write whatever I'm writing right now. Reactions. And these reactions, they are mainly classified into two types, right? Irreversible. And there are some which can be reversible. There are something which can be reversible. Now, the reactions which are irreversible, they only happen in one direction. That means, for example, if you have carbon and you burn this carbon with oxygen, you will get what? Carbon dioxide. Okay. Now, carbon dioxide and plus some heat. Carbon dioxide plus some heat. But you don't see that heat and carbon dioxide, they are again forming carbon and oxygen gases, right? You don't see that happen. You don't see that happening. But there are some reactions which are reversible in nature, For example, you have reactions such as hydrogen iodide. Okay, hydrogen iodide. What happens? Hydrogen iodide, it can dissociate itself into hydrogen, H2 and I2. Okay, and H2 and I2 can again, they can also combine together and they can form 2HI. They can also form 2HI. Okay. Now, we will be talking about reversible type of reactions and we will be thinking about equilibria in reversible type of reactions. Okay. Now, I also want to relate this equilibria in terms of in terms of the Gibbs free energy of products and reactions. Okay. So what is the Gibbs free energy of the products and what is the Gibbs free energy of the reactants? Okay. And where is this equilibrium state? Now, when you are going to talk about the Gibbs free energy of HI, we will not be talking about in terms of in 1 mole, in 2 mole, or in 3 mole. Okay. Now, whatever we will be talking about, it will be in terms of the questions, and we will be talking about in terms of what? In terms of experiments. Okay. So the whole chapter, it depends on what type of conditions you are taking, what is the amount of reactant you are taking, what is the amount of product you are taking. Okay, what is the amount of product you are taking? Now, I want you to tell me, now I hope this is going to be a bit logical only. Okay, now this is a plot. I would say this is a plot. Okay, this is a graph, and here let us say we have the free energy values. Free energy values. Okay, that is G, and of the reactants, let us say, and here we have the G, that is free energy of products. Okay, free energy of products. Now you tell me, if I take a large amount of reactant, then the free energy of reactant will be very high. Yes or no? The whole reactant. Okay, I'm not talking about per mole, I'm talking as a whole. If I take 1 kg of reactant, that means if I compare that to, let us say, half kg, then the energy in those reactants will be high. If I take more amount, yes or no? Guys?
Yes, sir.
Okay, logical. It doesn't break any logic, right? So again, we will have some reactant molecule. We'll have some reactant molecule. Okay, some reactant. This is the free energy of the reactant molecules. Okay, this is the free energy of reactant molecules. And let us say this is the free energy of, here is the free energy of what? Your products. Here is the free energy of products. Now, if the reactants free energy is very high, what will happen? It will try and it will achieve a lower ground. Now, as soon as it is progressing this way, this reaction time. Okay, the reaction time. What will happen? The reactant will react and they will try to form product. Okay, try to form product. So the free energy is going to decrease. Free energy is going to decrease. But there will be a point. After a point, you can see that the products is getting very large. It is getting very large, and since it is a reversible reaction, what will happen? Since it is a reversible reaction, what can happen? We can also go from this way. Right? We can also go from this way. Now, at this point of time, where the free energy of both, there are some reactant present here, there are some product also present here, but in total, the reactant and the product, they are in such a way that the whole free energy of this system, the free energy of this system is what? The free energy of this system is the lowest. Okay. Now, each and every system, it wants to lower its free energy. That is why if you have some reactants and product which can go towards with a reversible type of reaction, so what will happen? They will combine in such a way that the free energy is what? Free energy is at the lowest, and at that point of time, the equilibrium will be existing. Okay, at that point of time, equilibrium will be existing. Now you can also, that means you can start the reaction in any of the ways, right? You can start the reaction in any of the ways. You just take a ball, maybe. Okay, you take a ball and if you try rolling this ball down, it will come and reach here. So whether you start from the product or you start from the reactant, it is always going to reach an equilibrium state where the free energy is what is at the lowest. Okay, so keep this in mind that everything is happening in terms of free energy. And maybe if I have some time extra, but I don't think I will be having, it is already mid of January, I will be going deep into this free energy part. Okay, sometime later, but keep that picture in your head. Keep that picture in your head when you're thinking about equilibrium. Okay, now we understood that we will be only talking about the reversible reactions. Okay, and in the reversible reactions, we can achieve equilibria. Okay. Now let us write. Okay, now let us write. First of all, what is a reversible reaction? What is a reversible reaction? Okay, so please write. The reactions in which products can be, in which products can be, which products, which products which are formed can also react with each other, can also react with each other under suitable condition, under suitable condition, to give back the reactants, okay. That means, for example, you will have reactions such as H2 plus I2 giving HI. You can also have N2 plus 3H2. It is giving you 2 NH3 molecules. 2 NH3. Then also you can have N2 plus O2 giving you 2NO. And there is also one reaction which is important, that is N2O4. It can dissociate to 2NO2, and 2NO2 can also dimerize to form N2O4. Okay, so these are some reactions. These are some reactions which can in which the products, they can also react with each other, and they can also give back the reactants. Okay. Done?
Yes, sir.
Yes, sir.
Okay. Now we will be studying the equilibrium states. We will be studying the equilibrium states of reversible reaction. Okay. And we will not be studying the equilibrium state for irreversible reaction. Why is that? Because see, irreversible reaction, there is nothing to study. There is A, there is B. It is going to give you only C, right? Only C. But if I have A plus B, and it is going to give me C and 2 moles of C, and these 2 moles of C, they can also react with each other and they can form A and B. Now we have one question in mind. If I started with this much, I started with this many number of moles of A and B, and at equilibrium, you are saying that I will not get 2 moles of C, but I will rather get what? A mixture of reactants and products. Yes or no? That's what we are saying now when it is an equilibrium. Now we want to understand what is the number of moles of reactant and what is the number of moles of products. Now, you know, we can, if it was irreversible reaction, we can directly apply what? Stoichiometry. Hana? We can apply stoichiometry. 1 mole of A reacts with 1 mole of B to give 1 mole of C. But in this reversible reaction, what is happening? Not all of the reactant it is getting converted to the product. Some of the product it is also getting converted to the reactant. That means at an equilibrium, when nothing is happening, then I can say what is happening. If nothing is happening, then A plus B, which was giving me C, okay, which was giving me C. Now let's say 2 moles of C, and C plus C, it is also giving me A. It is also giving me A. So how do we show this reaction? We show this reaction by a reversible arrow like this. Now A to B is giving me C. This is forward. 2C is giving me A plus B. This is backward. Now when the rate of forward reaction is equal to rate of backward reaction is equal, then we say that equilibrium has been achieved. Because as soon as we had A, we added some B, we started seeing some moles of C being formed. Then we added some more B, and now we see what? And now we see that A and B, their concentrations are not changing, and the molecule and the C's concentration is also not changing. What does that mean? The reaction has stopped? No, the reaction has not stopped, but rather what is happening? The 2 C molecules, they are reacting together and they are forming A and B. So this is why we say that the rate of forward reaction, that means the number of A and B reacting, they are again being formed by the 2 C molecules. Okay, so you understand this idea about rate of forward reaction and rate of backward reaction is equal
Yes,
in
sir.
equilibrium?
Yes, sir.
All of you? Okay, fine. Okay, now let us say if the rate of forward and rate of backward reaction is equal, then what is the constant property? What is the constant property that we are more concerned about? So the constant in chemical equilibrium will be concentration, because the concentration A will not change over time and the concentration of C will not change over time. But does that mean the concentration of A and the reactants and the product is equal? No. Okay, so concentration of reactant is constant and concentration of product is constant. Okay, but it does not mean that the reactants concentration is equal to product's concentration. This is not the meaning of equilibria. Okay, what is equal? The rate of forward is equal to rate of backward. Okay, done. See, let us go back to the swimming pool example. Okay, let us go back to the swimming pool example. We have a swimming pool. Okay, we have a swimming pool. Now we say that there are 5 people. There are 5 people in the swimming pool, and outside the swimming pool, on an average, there are 10 people over the day. What does that mean? It means that the rate of in and the rate of out are equal. It does not mean the number of people inside the swimming pool and the number of people outside the swimming pool are same. Similarly, if I go from the reactants A to reactant B, and B is also getting converted to A, it does not mean that A and B are equal. It does not mean the concentration of A and B are equal. It just means that the rate of in and rate of out are equal. You got this? Yes or no?
Yes, sir.
Yes, sir.
Okay, fine. Now let us write characteristic. Okay, when is we have to discuss this now? When is the equilibrium attained? So what is the topic that you have written? Equilibrium. You're writing under that topic? Yes or no? Equilibrium only, na?
Reaction.
Irreversible reaction. Okay, fine. Now write attainment of equilibria. Equilibrium. Okay. Who will answer me? I have A. Okay, I have A, and then I added B, and I am going to get C plus D. Okay, so initially, if I will say initially what is I'm here writing the rates. Okay, I'm here writing the rate, and here is the time. Okay, so Matthew, you will tell me when we don't have any product, okay, we don't have any product. Now when we started the reaction, there is some rate of forward reaction. Yes or no?
Yes, there is a rate of forward.
There is a forward reaction. Okay, so there is a rate of forward reaction. We'll start from here. So there's some positive rate of forward reaction. What is the rate of backward reaction when there is zero product? When there is no product, the rate of backward reaction will be 0.
Yes,
because
0.
no reaction
Yeah, because there's no product. Yeah.
Yeah. So slowly what will happen? The rate of forward reaction, it is very high initially, but as soon as the reactant will get consumed, slowly the rate of reaction will also go down.
Decrease, yes.
Yeah, decrease. Okay. And it will achieve a constant value like this. Now, similarly, what will happen to the rate of backward reaction? Now, since as the products are being formed, the rate of backward reaction will increase. Yes or no?
Increase, yes, it will increase.
It will increase. Now, when the rate of backward and rate of forward reaction, they have achieved a same value, this is what we will say that this is the equilibrium state.
Yes.
This is the equilibrium. Okay, this is the equilibrium. Now, in this case, what is happening? The rate of forward and the rate of backward is same. Okay, rate of forward and rate of backward is same. But let us see what happens if I talk about the concentrations. Okay, let us talk about the concentrations also. Let me just move these things a bit. I need another graph here. Okay, now here I am writing the concentrations. And again, here is time. Here is time. Now, initially, when we had the concentration of the reactant was something because we started, and slowly what happens, the concentration of the reactant, it decreased, right? It will
Yes.
decrease. And it will attain a constant value like this. It will attain a constant value.
Mhm.
What will happen to the products? What will happen to products?
It'll be constant at one point.
Yeah, it will increase, right? And it will be constant
Mhm.
after a point, right? After a point, it will be
Yes.
constant.
Constant.
Now, please remember that when it is getting constant, okay. So this is a line here. This is a line here. Oops, I need a blue pen for that. Now, at this point of time, I will say, now whenever the change is happening, that is not equilibrium. Now, when the concentration become constant, okay. Now here the concentrations are constant, right? Now at this stage, I will say that this is
Equilibrium.
Yeah, this is equilibrium. Okay. So A plus B, and then we write C and D in yellow, so that the reactant, and this trend line is for the product. Okay, now again, I am emphasizing on this point that the reaction has not stopped. Okay, it has just reached equilibrium. That means we cannot see any measurable change in the concentration. It does not mean the reaction has stopped. Okay, please remember that point. Let me know if you're done writing this graphs.
Done, sir.
Done, all of you?
No,
All
sir.
right.
No, sir. One second.
Okay. Fine.
Yes, sir. Done.
Right, next. Characteristics of equilibrium. Yeah. Characteristics of equilibrium, or rather chemical equilibrium. Characteristics of chemical equilibrium. Number one point is chemical equilibrium is dynamic in nature. Chemical equilibrium is dynamic in nature. Meaning the reaction doesn't stop. Reaction doesn't stop. Okay. It's just that there is just that the rate of forward reaction is equal to rate of backward. Okay, rate of backward reaction. Now, next is the properties of the system remains constant, remains unchanged, I will say, remains constant at the equilibrium okay, and remains unchanged after that. Okay, and remains unchanged after that. Right, the third point. Equilibrium can be attained only in closed system. Right, because if we have an open system, then what will happen? If we have an open system, then more reactants or products can be added, and then the equilibrium can be, then the equilibrium will not attain. For example, if we have some reaction in which gas is forming, we have an open system, then what will happen? The gas will escape out, then the reverse reaction is not possible, and the reverse reaction will not be possible. That is why equilibrium can only be attained if we have a closed system. Right, the fourth point. Equilibrium can be achieved from any direction. Equilibrium can be achieved from any direction. Now you can remember that ball point, right? Because equilibrium is the point when we have the lowest free energy. So it doesn't matter whether you are starting from the reactant or you are starting from the product. What will happen? You will be achieving the equilibrium no matter what. Okay. So please write the equilibrium can be achieved from any direction. That is, it can be either achieved from the products or, and it doesn't matter where you start from. It doesn't matter where you are starting from. Right, the next point, that is fifth point, the last point of characteristic. The catalyst doesn't alter the equilibrium point. It doesn't alter the equilibrium point. And catalyst, what does it do? Catalyst has a relationship with time. Okay, it does not have any relationship with energy. Okay, that is one thing that you can remember about catalyst. Do you know, have you ever used the word catalyst in a general English form? The sense, no?
Yes, something that makes anything faster.
Faster, right? So it does not. So what will happen? Equilibrium will be achieved faster. But the point of equilibrium, that means, what does the point of equilibrium means? Point of equilibrium means what, first of all, what property you are choosing to define the equilibrium. For example, in chemical reaction, we'll have the concentration. So equilibrium point in chemical equilibria, it means the concentration, the equilibrium concentration, they will not change if you're adding a catalyst. Yeah, obviously, those equilibrium concentration, they can be achieved faster, but those concentration will not change. That means the equilibrium point will not change if we add a catalyst. Write this reaction. Let me know if you're done.
Done, sir.
Then all of you, oh sorry, reaction, I'm saying the point. All of you done?
Yes.
Done. Okay. Wait a second. Can you see this?
Yes, sir.
All of you? Yes. Samaira, Mariam. Mariam to say that. Right? Yes, Samaira, Matthew, Aisha.
Yes, sir. Yes, sir.
Yes,
All of you can see this? Okay. Now, in this table, we have taken some initial concentration. Okay, we have taken initial concentration of NO2. Okay, NO2 at equilibrium and N2O4. So essentially, what I am saying that we are having a reaction. We are having a reaction in which okay, I need maybe what I can do is I can copy this and I can maybe play this in the one note only. I think that will be better. Let me see if I can. Yeah, so it got pasted like this only. That's good. Can I move this? Yeah, I can move this. Okay, fine. Can I increase the size? No. No, I cannot increase the size. Okay, fine. No problem. So we have a reaction in which we have, please don't write these things, okay? So initial NO2. So we have NO2, it is getting converted to N2O4. So keeping my stoichiometry right. So this is the reaction that is happening, right? Any problem? No problem? These are the initial NO2 concentration. We took NO2 initially, okay? Then we kept it for a while. And then we saw when we took 0.142 constant, that is 0.142 molar of NO2. Then at equilibrium, I had 0.042 moles of NO2 and 0.1 mole of N2O4. Okay. Then when we took 2 moles, or rather 2 moles per liter, 2 molar NO2, I got 0.051 moles. Sorry, 0.051 molar NO2, and I got 0.149 molar of N2O4. You understanding what is happening in the table? Yes or no? Tell me. No? Yes? Matthew. अरे भाई आप लोग कुछ बोलिएगा तभी तो हम आगे कुछ बता पाएंगे ना
Yes,
इसमें।
sir.
हमें तो सब समझ में आ रहा है ना? हमको तो समझ में आएगा. So this is the first experiment I did, okay? Then in the second experiment, I took 0.2 molar NO2. In the third experiment, I took the concentration 0.3 molar. And in the fourth experiment, I took this 0.5, and this is the sixth experiment I did. Now, in each of these experiments at equilibrium, I kept the NO2 as it is, and then after that, I measured the concentration of NO2 and N2O4 after a very long time. When the concentrations of NO2 and N2O4 became constant, I told that okay, fine, this is my equilibria. Now I will measure what is the concentration of NO2 and what is the concentration of N2O4. So I got these values. Okay, I got these values. Now I was trying to check that whether does these value they have any relationship or not. Okay, they have any relationship or not. Now you understand what is happening here. So I can move back to I need Excel. That is why I shared the Excel file. Right. So we now want to see what is the relationship between these two things. Okay, what is the relationship between the concentration at equilibrium, okay, and the concentration of NO2 and the concentration of N2O4 at equilibrium. So one thing I can do is that I can plot this, right? So let me maybe plot this thing and see. All right. So you can see there is some kind of trend, right? It is not a straight line. Yes or no?
Yeah, it's an upward trend.
It is an upward trend, obviously, because if we are increasing the concentration, then on the x-axis, what do we have on the x-axis? On the x-axis, okay, I can write here. Wow, this is good. On the x-axis, we are starting with here, no? We're starting here, that is 0.42. So in the x-axis, we have the concentration of NO2. And in the y-axis, what do we have? We have the concentration of N2O4. Right? We have the concentration of N2O4, and I'm plotting.
Yes, sir.
Okay, I'm plotting this. Okay. Now, the next thing I can say, do you see any relationship here? 0.1, 0.42, 0.149, 0.51, any relationship? The reaction, what did we have? We had 2NO. 2 is giving me N2O4. 2NO2, it is giving me N2O4. Let me do one thing. Okay, let me see. You cannot find. Let me see. It is obviously initially it may be seen that it is double, but it is not double, right? It is not double, correct?
Yeah, it's not double.
It's not double. Let me do one thing. Do you know how to use Excel? No or yes? No. And let me square this term. So I'll write the square of okay, this is not a square. This is not the square of N2O4. Now, anything else that I can see? Wait a second. Let me see if I can plot a value. I cannot plot a graph here. I need a line. Okay, I need the expression for this line. It would have been very good if it directly gave me a line somewhere like that. Okay, chart option is there. Quick layout. No, I don't need a regression line. Again, a regression. No, I don't need that. I don't need that. Okay, so can you see that it is somewhat exponential? Yes or no?
Yeah, somewhat.
It is somewhat exponential, right? So there is some, I can do something, I can multiply some value because it is not exactly exponential. Let me, how are the exponential graph? The exponential graphs are like this. Exponential graphs are like this, right? Exponential graph are like this.
Yes.
Now, our graph is how? Our graph is? Our graph is like this, correct?
Yeah.
So there is some value that has been multiplied to both the x and y's, and if you plot it, like this, this was our graph. Okay, this was the x-axis where we had the concentration of NO2, and here we had the concentration of N2O4. Okay, now if I would have been able to actually get the exact equation for this type of curve, it would be somewhere, it would be something around, this is my x-axis and this is my y-axis. So y, it is exponentially, right? So I can see it is directly proportional to the x of x square. It is directly proportional to x square, right? And I can say y is what? It is equal to some constant into x square, y into kx square. Okay, now let me see if I can show you something which is like that. So y, it is equal to kx to the power 2. Yeah, can you see this? Tell me.
Yeah.
It is somewhat like that. Now we are starting with from here, right? We're starting from here and we are going upward trends like this, correct?
Yes.
Okay, so you can see that it is kx square, right? Y is equal to kx square. Now let me go back here and let me see. I can also say that the concentration of N2O4, it is equal to the concentration of N2O4, that is the y-axis. It is equal to some